Right. Yeah. Lecture 14. Okay, as a reminder, homework 5 due Sunday. And midterm will be posted early next week. Yes, we're gonna fix it. We're gonna fix it early, like Monday or Tuesday. Oh, I was preparing. Uh, you can begin anytime. Just make sure that you give it back to me within a week. Yes, it's a more comprehensive one. Typically, we do it in class though. Mm, Comprehensive is defined as homework 1 to homework 5. Anything on the homework is a fair game, at least for me. Maybe not for you. How many questions? I think there are 6, but there are some tiny questions, like sub question. There are 6 questions. It's a time limit. Make sure you do it before Sunday. You don't have to time it yourself. Make sure you hand it in before the deadline. There's an upper bound, but there's no lower bound. Okay. So, any other question regarding the midterm? Yes, if you know what to do, you should finish it in 2 to 3 hours. That's all. It do even like take less time than the homework. If you know what you're doing, it take you 2 or 3 hours. Because you did it before, guys. You did it before, right? It's not like you learn it the first time. You do the homework the first time, it's so hard. Like you're programming on homework, you did it the first time, it's so hard. But after you did everything, you come back and like, why did I take time to think about it? And so on. Okay. Any other question? Any other question? Okay, so today we're gonna learn a bit more about counting. Okay, so last time we learned the official name is called multiplication. I call it common sense multiplication, right? That if we have choices, we can multiply the choices. We learn addition, right? We count two things, we add it together if they don't intersect, right? We learn how to do subtraction. Okay, so let's start off easy. Let's start off easy. Let's start off easy. So for example, you know, there are something annoying about password, right? Every single password provider give you like different requirements. Some require like capital letter, at least one, right? Some require numeric, right? At least one, and they may require the length, at least 8 or something, right? And it requires some special symbol. It's annoying. Every website use like different standards. Okay, So we're gonna count something easy. So let's say 8 alphanumeric. Okay, that means lowercase a to z, a to z, if you know regex, and then 0 to 9. Okay, 8 alphanumeric and require at least one number. Anywhere. How many are there? Okay, you got the idea, right? So for example, A, terrible password, but that counts. But that doesn't count. That doesn't count because there's no number. If you have A1, that counts. If you do 1 and then A, B, C, D, E, F, G, that also count because there is at least one number. Okay, I give you 3 minutes to think about it. Okay, how many are there? Our one. Yes, that's a valid. At least one number. And that's exactly what I'm going to ask next. What if you also require at least one alphanumeric? At least one number, yes. So what Tanaka said is valid too. Like 0, 1, 2, 3, 4, 5, 6, 7. This is also valid. At least one number. Okay, I give you 2 minutes to think about it. Set 10 times 23 times 23. Just give me your answer first. Don't tell me why yet. Just tell me the answer first, and then I'm going to ask you one by one. But by the way, there are how many characters? 26 characters? 26, right? A to Z 26, and there are 10 here. There are 26 English character. Okay. And 25, 25, okay. Okay, guys, why is there only 7 number? Okay, now what said 61 to the 7 times 9 square? That's from now what? Any other answer? I noticed a pattern with my handwriting though. If I am like, if I pass through like 6 meetings before this class, then my handwriting gonna look like this. But bear with me. Now what? Okay. So, okay, Heath said 62 times, so close. 61 times, this is close though. I can tell you it's not entirely correct, but it's close. We're gonna learn this expression later. That really long thing. We're gonna learn that later. And 52 times 51 times 50 times 49 times 48 times 47 times 46 times 45. And that one is from Keith. And there is Alexi. 25 to the 7 multiply by 10. Okay, interesting. So I can see, like almost most of you are thinking about it as a constructive counting, right? So you try to count it in one swath, and that's Pong Shai. Thank you. 62 to the 9. Okay, by the way, none of it is correct, but that's okay. That's okay because we're gonna learn how to fix it. Okay, so let me try to separate your answer into two types. The first type, right, is the way that you count it constructively, right? You try to construct things exactly correctly, even though you all get different answers, right? You try to construct them from ground up, right? So you try to see. So most of you try to do the following. Okay, you try to construct like how many choices are there for the first one, how many choices are there for the second one, how many choices are there for the third one, and so on, and up to the ninth one, right? I think that's what everyone's trying to do. How many choices are there for each one of them? However, that problem, right? That problem gets really hard. You can see there are so many different answers because of this constraint. Because of this constraint, at least one number, right? It makes constructive the construction, the way that you do it, you try to count it constructively, make it really hard because you try to enforce the constraint while you're picking them. And that constraint is actually pretty hard to construct, right? Because at least one number, then you start to have an if statement, right? If you pick, if you pick a letter, then it's okay. If you start, you want to make sure that you pick at least one number, right? If you try to pick it constructively. So let's do the simplest one. The simplest one, if you try to do this, is you can try, okay, Ajahn, there are 8 slots, right? Okay, there are 8 slots, and each slot, let's ignore the constraint. Let's ignore the constraint. Okay. Let's ignore the constraint. Then you're gonna count that, and there are what 62, right? Why 61? I don't get it. At least you have 62, and there are 62 to the 9. I don't know how you get the 9. But the total, right? There are 62 to the 8. That's quite clear, right? Also for Keith, 62 to the 8, right? Okay, everyone clear, right? But 62 to the 8, you overcount a whole bunch of things, right? Right? But 62, you're gonna say, what's wrong with 62 to the 8 though? Can you tell me? What's wrong with 62 to the 8? What's wrong with 62 to the 8? We get 62 to the 8 from the fact that there are 62, right? So this one, right? They're very good. Very good. So 62 for each choice of them is not entirely correct, right? Because there are the one that is valid, and there's the one that is not valid. We get, right? There's the one that's valid and the other one that's not valid. But if we can count the invalid one, if we can count the invalid one, and if the invalid one is easy to count, then we are good, right? So what do I do? What do I mean exactly by invalid though? What do you mean? Doesn't have at least one number. So that means there is no number, right? No number. Can we count this? 8 digits with no numbers. We can. How many? Not 62 anymore. I don't know why you get multiplied by 10. Thanatat said, okay, Ajahn, that's easy. Just 52 to the 8, right? Because these are all the lowercase and uppercase, 52 to the 8. Okay. So that's good. 52 to the 8. So that means all you need to do, right? If you just want the valid, what do you do? If you just want the valid one, so how many of them are valid? Very good. Just that 62 to the 8 minus 52 to the 8. Just subtract it, right? Everyone see, right? This is like a trap when you try to think about this kind of problem. I want you to view it in like different method. If you try to do them constructively, like how many choices are there for the first one, how many choices are there for the second one, sometimes the constraint is so complicated for you to make a constructive rule. But if you decompose it into like the valid, not valid, and then you start to add them up, right, or subtract them off, then the problem becomes a lot easier, like this one, right? When I tell you how would you count, it becomes a lot easier. Any questions so far, though? Any questions so far? Okay, so let's do another example. Let's do another example. Someone said earlier, I don't remember who, but you know that this is a turbo password. The one without the this is a turbo password, right? The one without the letter at all. Okay, so we want to make sure, what if we do not count this one? That's good. What if we do not count this one? So that means 8 character, at least one number, and at least one character. Okay, alphanumeric. By the way, just to tell you, 8 character, you can actually crack it on GPU within like minutes. You can crack it on GPU within minutes, which I'm not sure which course we have in writing program for GPU. Pretty useful though. I never learned it. I tried to learn it, except I gave up with Windows. Okay, I give you 2 minutes to do it. At least one character. So it's A to C, A to C, and 0 to 9. Okay, there is C. 62 to the 8 minus 52 to the 8 minus 10 to the 8. Anyone else want to try, Keith? There was someone who said minus 10 to the 8. Saran as well, right? Is that raising your hand or not? What? Okay, and risky. Okay, so I think this one is pretty easy, right? By the same idea. By the same idea that you just subtract off, right? That there is the valid one. There is also no number. There is also the people with no character. And we can count each one of them, and there are 10 to the 8 of this guy, so you can subtract it off. Okay. Okay, so this one is easy. So let's try the next one. Let's try the next one, which is related. Which is related. Okay. How about how about 10 length 10 binary string? Okay, length 10 binary string. That means it's like 0 and 1. There are 10 of them. Okay. And I want to ask how many start with 1 or n with 0, 0. Okay, what that means is the following. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That one counts because it starts with 1. Okay, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. That one also counts because end with 0. Okay, this one also counts. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This one also count because it does at least one of them. So the keyword here is or. Okay, this one doesn't count the 0 and then end with 1. Doesn't know. Okay, how many are there? You have 3 minutes to think about it because we want to go on and do something fun. I can tell you there should be no factorial, right? We're not trying to rearrange anything. There's no factorial. Okay, there is 7. 2 to the 10 minus 2 to the 8 minus 2 to the 6. Okay, so that's 7. Yeah, there should be no factorial. Right, by the way, the total here is 2 to the 10. Total there is 2 to the 10. That is Alexi. 2 to the 10 minus 2 to the second minus 2. And that is Noah. You can see all these look really close to each other. Minus 2 to the 7. And Pongshai and Keith. It's 2 to the 10 minus 2 to the 8. Okay, so close to 7, right? Okay, that's it. So tell me one by one, because you can see that everyone try to subtract something and add something, right? So let's start with this answer. This one is interesting. 2 to the 10. Okay, I think everyone is clear, right? 2 to the 10 is everything. What about 2 to the 8? Where does it come from though? 8 Pongchai. Okay, that's also risky. 2 to the 10. Okay, we're gonna figure out what is 2 to the 10, 2 to the 9, and 2 to the 8. Minus, minus. Some answer may not look the same, but they are the same. Okay. I think everyone agree. 2 to the 10 is everything, right? Can you tell me what is 2 to the 9? For those of you who tell me 2 to the 9, what is it? There are so many people who say 2 to the 9. What is it? Oh, 1. So this is start with 1, right? Okay. How about 2 to the 8? What is it? For those of you who say 2 to the 8, end with 0, 0. Okay. 2 to the 6 and 2 to the 7. I'm not sure what it is. Okay, let's do 2 to the 7. Anyone? 2 to the 7. What is it? For those of you who have 2 to the 7. Very good. Start with 1 and end with 0. So you essentially you fix 3 position, right? You fix the first one and you fix the last one, and then you can change everything in between. So this is start with 1 and with 0, 0. Okay, so that's good. Everyone agree, right? So you can count a lot of things. Now, your job is to combine them. Your job is to combine them to get this. Okay, so let's think about this. Let's think about this. Okay, so there are three to four things. So let me actually copy this to the next page and now explain. Copy. Okay. Everyone tries to do the same thing except they combine it in different way. So let's look at how we would combine them. Okay, so there is everything. Okay, actually this is a bad idea. There is everything. Let me draw it this way. There is everything. Okay, this is everything. This is 2 to the 10. Okay, and then when you count, start with 1, right? So this is start with 1. With 1, and there are people who end with 0, 0. Okay, and there's a guy in between. So this thing is 1 and then 0, 0. Okay, and let's put in all the numbers. So the circle here, let me put it here, is 2 to the 9, right? That 2 to the 9, it includes the thing here as well. And oops, sorry about that. And that thing here is 2 to the 8, and the thing inside is 2 to the 7, right? Everyone clear, right? This is what everyone try to count, and we want to combine. So the thing that we want, right? The thing that we want is here, right? This is the thing that we want. It's inside the thing that I highlight. Okay. Why would you start at 2 to the 10, right? You don't really need this number. 2 to the 10 is not needed, right? So you can first start trying to count something close. So for example, you can start with 2 to the 9 plus 2 to the 8. Okay. 2 to 9 plus 2 to the 8 is close to what you need, right? Except you're gonna notice a dan, but you count the intersection twice. Yes. So you count this thing once, you count this thing once, but you count this thing twice. That's not what I want, right? What we want is to count it once. So what do I do to make sure that I count the thing inside once? Why is that times 2? Right? So this thing is this guy plus this guy plus this guy plus this guy. But what we want is only these 3, right? What we want only these 3. So what do I do on both sides, right? So what we do on both sides, we should subtract off this guy once, right? So that this guy cancel and we have what we need, right? So that means what you should subtract is only 2 to the 7. Are we good? Right? You subtract it off only once, because if you subtract it twice, you get rid of all of them. That's not what you want. You want to subtract it off once. Okay, so you learn another rule. This is called a subtraction rule. If you overcount something and you know exactly how much you overcount, there's no prize though. If it's a real class, then I give you some candies for giving the correct answer, but I give you some candy for giving the wrong answer anyway. Okay, so this is how much it is. So you learn one thing, that if you overcount something and you know exactly how much you overcount, all you need to do is subtract them off and then you're done, right? Okay, any questions though? Any questions? Okay, any questions? Okay, now you learn this. How about this? How about this? We're gonna overcount something like crazy as well. Okay. The idea here that I want to show you is the following. You have a chessboard. Okay, you have a chessboard. You know, this thing is 8 by 8. Okay. And then what you want to do, 1, 2, 3, 4, 5, 6, 7. Actually, I have a wait, what? I have this. Okay, there's an 8 by 8, 8 by 8. Okay, so this is the chessboard. You want to place rook, two of them, and they look the same. They are both white. Okay, such that they do not eat each other. They are not in each other ways. Are we good? So the idea here is if you place the rook, so you make two rooks, do not share row nor columns. How many ways are there to place them? It's 8 by 8 though. The chessboard is 8 by 8. The problem is you have two rooks. You want to place them on the chessboard such that they do not share the same row nor the column. So this is good. This is bad. Let me show you. This is bad if you share the same row. This is bad. This is also bad. This is also bad if they share the same row. So how many ways are there to place the rooks? Okay, I give you 3 minutes to think about it. If you can figure it out in 3 minutes, then I'm sorry. Sometimes you don't see it at the right angle, then it's gonna take you like forever. Do I know how to play that game? No, I don't. I know some of the rules. I know some of the rules, but I don't know all the rules. Max, you know, your Lumpi, Max is a really good chess player. Your Adan Jack is also a professional chess player. You can try ask him to play chess with you. 32, okay. Adan Jack is also a chess player. I think we even have chess club until COVID. Anyone else? I don't know where you get 32, but it sounds about right. He beat me within 5 minutes though. I don't know the rule. That being said, however, when I was undergrad, one of my homework is to write a chessboard with Minimax, and I won the competition. But I don't know the rules. But I seriously don't know the rule. Oh. Wait. Saran, I'm sorry. I'm gonna skip your thing. I'm gonna give your thing. Too hard to write. Wait. Alexi, you really meant the following? 8 by 8 square, or you mean only 8 square though? Minus 1. Minus 8 by 8. 64 square. I can understand 64 square, but I don't understand minus 1. Okay. So let's think about how we would do this systematically. But if you give me answer with 32 and 49, I have no idea how you got them. 49, I can guess is 7 by 7. But 32, I don't know how you get them. Might be correct though. I look at the answer. No, it's not correct. Okay, Alexei change. Oh, that's the same thing, right? That's the same. That's the same. 64 over 2. No. Okay. So let's look at this problem. I think for everyone that think about it, it's hard because of the following, right? It's hard because of two roots are like the same, right? The fact that two roots are treated the same, that makes the problem like a lot harder. When you see the problem, actually it doesn't make it much harder to count, but it make it much harder to see the problem. What if I tell you that these two roots are not the same? Like one of them is white and the other one is black. Would that make the problem easier? No? Okay. No? Really? So let's think about this. Let's do it systematically. Alexei was close, but not quite. Alexei was really close. That crepes is tasty. Yes, I'm hungry. McDonald's, by the way. Grab has 80 baht discount when you order a lot. Okay. Let me ask you, what if I only have one group? How many ways are there to place them? One group. Right. Let's look at this. If I only have one group and it's white, how many ways are there to do it? To place it on the board. How many ways are there? 8 by 8. Everyone's clear on that, right? If I have one group, that's what you would do. Okay, one group is 8 by 8. Okay, another group. How many ways are there to place them? Another group. To make sure they don't share the same row or column. To make sure with the condition is easier actually. With the condition, so think about this. So that means once you place the first group, right, this row is bad. This row is also bad. How many choices are there left? How many choices are there left? Seven square, right? So root number 2. Okay. What should I do with the 2? There are this many ways, 64 ways to put the root number 1. There are 49 ways to put root number 2. What should I do with them? Should I add? Should I subtract? Should I what? What should I do? What should I do? 8 by 8 and 7 by 7. What should I do with them? Multiply, right? Because given root number 1, I have this many ways to place root number 2. So you should multiply them. Is everyone good on this point? Everyone good on this point, right? But there's a tiny problem, right? There's a tiny problem that if that we overcount something, right? That this case where the two roots are here and there, right? And if R1 is here, R2 is here, right? That also include in this guy, right? That's also includes in this guy. So you place R1 first, and R1 is right there at wherever R2 is, and R2 is right there at wherever R1 is. So that means we overcounted. So how do we fix this problem though? How do we fix this problem? We just divide that by 2. Okay, now you learn a new trick. If you know how many times you overcount, you just divide it away, and then you're gonna get the correct one. Yes, you forgot to place the second root. Why is it overcounting? Good. So let me show you. Let me get a bigger board. Okay, it's overcount because 8 by 8. Oops, sorry. When we say 8 by 8 multiplied by 7 times 7, right? There is this one, and there is also this case, right? Right? You count them twice. Right? If it's the same color, then you just divide that by 2 because you only count it by a factor of 2. Everyone good? Because you overcount it by a factor of 2, then you just place them by 2. Okay, everyone good? Let's do something harder. Let's do something harder. Keith, are we good? Keith, are we good? It's actually this kind of counting for Keith and for Risky. For Keith and for Risky, this kind of counting typically come up when you try to count entropy, like how many numbers of states there are. And then you need to count it correctly within the factor of 2. Okay, so next one. How about if we have 2 rooks, same color, and we also have 2 bishops of the same color. 2 bishops of the same color. And I want to make sure none share the same row, no columns. So this is good. This is bad. So if you place the bishop here, same color, every bishop here and there, rook and bishop are different, but bishop are the same. This is bad because they share the same row. Okay. How about if you have 2 rooks, 2 bishop, 2 rooks, 2 bishop, none of them share the same row nor column. How many? You're going to learn how to think about it systematically. And it has a friend for bishop. Okay, that's actually yes and no. That's actually yes and no. If you think about it, right, counting is sort of recursion. Right? You remember that when we counted stair, a lot of counting problems you can write as a recursion. And then you solve the recurrent, but I'm trying not to go there. I try not to go there. I think Ajahn Kanat will help you do it once. So there are some answers powering in. So let me write them down. So that's Saran minus the bishop. Okay, I'll tell that, and I'll call that a non-answer. And Alexei and Keith are exactly the same one, right? By 5 square divided by. Faster. Okay, so this is the same idea, right? This is the same idea. I think everyone can guess this guy, right? The reason that I asked you twice is because I want to make sure you know how to do the second one. The first one will get you to think about it. Okay, so this is the following. That it is, I think everyone knows the top, right? The top is like if everything were to be different, right? If everything were to be different, that's the top part. Right? If everything were to be different, then this is the top part. But then you can switch the 2 rooks. So that means at least you overcount that by a factor of 2. And you can switch the bishop. So that means you overcount it by another factor of 2. So in the end, it's going to be 8 square, exactly that answer. Right? Because you overcount rook by a factor of 2, you overcount bishop by another factor of 2. Okay. Any questions so far though regarding this one? Before we do the next one. Still confused how overcount works? So let's think about this. How many cases are there? Okay, let's think about how many cases are there. Good. Just ask though, just ask, because this chapter you can say is the hardest and it's the easiest as well. Rook cannot be in the way of bishop. So let's think about how much we overcount. How did I get 4, right? So for example, so this guy, you have 2 cases, right? You have 2 cases where you can switch R1 and R2. So you have R1, R2, and B1 and B2, whatever the position is. First, you can switch this guy with that guy, and you can switch this guy with that guy. So there are 4 ways you can do it. That you're gonna overcount. Someone get? Right. Is it better? You can switch the rooks and can switch the bishop. Kind of no. Okay, let me try again. Let me try again. Let me try again. Okay, let me put B2 over here. Okay, the top one, the top part is when everything is different, is everything is the right? But once you place them, you know that when you count the thing on the top, you also count the following case. You also count the following case R2 and R1. And also let's make sure this two are the same, B1 and B2. Right? These two are exactly the same thing. Right? These two are exactly the same thing. That is why we divide by the first two. Okay. And for each one of them, because you place 4 pieces, and you want to make sure that none of them share the same row nor colors. Right? This guy, okay, so let's do it again. So this guy is clear that he has 64 choices, right? Ignore everyone else. Then the second guy, because the first guy bans 1 row and 1 column, you have 7 by 7 choices left for the second guy. Right? So for this guy, now it's going to be down by 6 by 6, and this guy going to be down by 5 by 5. How are we good? We already baked in the fact that you do not share the same row nor columns. Okay, but by doing that, we also double count like crazy. Okay, any other question though? Any other question? Good question, by the way. Any other question? Okay, so let's do the next one before we take a break. Okay, before we take a break. Yes. Yes, bishop 1 has 6 by 6 because you already placed this and that, right? You ban 2 columns and 2 rows. You ban 2 columns and 2 rows. So let's think about this. Okay, you have a round table. Yes, bishop and rook do not move in the same way. I just say that you place something that looks the same on the board. Okay, let's say you have a round table. Okay, there are, let's say 10 students. Student number 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so you want to seat 10 people. Okay, let's say that's what's the game name now? What's the game name? Among Us, no one plays it anymore, right? Okay, so there are 10. Okay, there are 10 seats, right? And then there are 10 students. Yeah, there are 10 students. And we sit them in a round table. What that means is the following. What that means is the following. There is some circular symmetry. So this one, and let me see if technology works. And can I rotate? Is there a way to rotate? No. So this one and this one rotate a little bit are the same thing. So what that means is the following. let me just write 10, 1, 2, 3, 3, 4, 5, 6, 7, 8, 9 are the same. Right. Resize, does it let me rotate though? Does resize let me rotate? Oh, it let me rotate. Oh, wait, technology, thank you. Okay, so these two are exactly the same, right? Even though you rotate one by just a little bit. Okay, so the question here is, so the question here is, how many ways are there to sit them? How many ways to seat them in a round table? Okay, how many there? How many ways to seat them around a round table? Seat that 8 factorial is seat. Anyone else? How did you get 100? 10 by 10. 10 factorial, 9 factorial. Let's say this is risky, and this thing is Justin, and 9 factorial is now what? And this cluster run. Okay, so let's look at this. Let's look at it. Let's start with this. I'm just going to, Risky, you're going to see where you got it wrong. Okay, 10 factorial. How did you get it though, Justin? How did you get it? How did you get 10 factorial? What is 10 factorial? Okay, good. Right? Okay, so yes. So 10 factorial is a permutation of 10 to 1, right? Okay. The guy number 10 to the guy number 1. So you can think about them as like rearrange them in a straight line. So yes, the first one, the first guy has 10 choices, right? He can pick any seat. The second guy had 9 choices and so on. So that's a 10 factorial, right? But that 10 factorial, I think it's clear to you that you also overcount, right? You count these two guys as a different one. That's the 10 factorial. Is someone clear on that concept? Or 10 factorial, yes, you count each one of these as different ones. So how do we fix it? How many times did you like overcount? Very good. Because once you pick a seat, right? So given this guy, there are 10 copies because you can rotate it 10 times. Right? You can rotate it 10 times. So that means it's going to be 10 factorial over 10, which is 9 factorial. Right. So it becomes 9 factorial. Yes. Another way to think about it, is to anchor some guy to the sheet, so to the seat. So for example, you fix number one cannot go anywhere, and then you let arrange the rest as well. That works too, right? That way you don't overcount at all. There are many ways to reach exactly the same answer. Right, we can fix the head and then let the rest rearrange. So that means this guy will never get counted. Okay, so that's another way to think about it. So that means you just rearrange the last 9. Okay, so any questions so far about this one though? Let me ask you a quick question. A quick question. How about this? How about this? How about this? What if? What if the same rule? 10 students. How many ways to sit around the table? Except this guy, number 1 and number 2, they love each other so much. They need to sit next to each other in any particular order, though. So that means it could be like 2, 1, 1, 2. But they have to sit right next to each other. Okay. So 10 students. Number of ways to seat them in a round table. But number 1 and 2 need to be next to each other. Okay, everyone got the same answer, right? It's 8 factorial multiplied by 2. And the reason, there are many ways to do this. This is one way, right? You can lump number 1 and number 2. Just call one number 2 just one person, right? You can call this is one person. 3, 4, 5, 6, 7, 8, 9, 10, right? Then you have 9 person left. You see these 9 person around table. We know by that there are 8 factorial of them, right? Because you have 9 people. And then you can unpack this guy. There are 2 ways to unpack. It's either 1, 2, or 2, 1. So that's multiplied by 2. So so you pack and unpack the same idea that we had before. Okay. Any question though? If not, we're gonna take 10 minutes break and we're gonna come back and do something even more complicated. Okay. Now that you know division rule, you can do a whole bunch of things. Because we don't want to overcount, right? For all the rotation, Keith, for all the rotation of this, there is exactly one way where one sit there, right, Keith? So that means if you fix one, you will count all the rotation as one, right? Right. This is the idea. For every rotation, there is only one rotation that one sits there. So that means you do not overcount it by a factor of 10 if you fix some seat already. I'm gonna solve you another mystery because I'm sure when you learn probability or counting in high school, no one actually tells you this. But come back in 10 minutes. 1507. About Hanoi right now. I haven't watched it. I have too many things to do. What about it? If you learn how to appreciate things on Veritasium and number file, then I think I succeed in teaching the courses. You get to appreciate a lot more like more fundamental math that there may it might not be apparent to you that there is a use for it. No, I haven't watched it though. Why fixing the head work? Yes, it works this way. So think about this. Let there be only 3 people. Number one, let them sit on a trifasting. 1, 2, and 3. Okay, so the number of ways you can overcount this, there are 2, 3, and 1, and 3, 2, 1, right? And also another way that looks different, right? 2, 1, and 3. These two are not the same, clearly not the same, right? If you read like this, okay, then there are going to be 3, 2, 1, and 1, 3, 2. Okay, so to put 3 people on in a circle, then there's only 2 ways. Okay, and the reason that I'm trying to show this is the reason that fixing one works is because for each one of the combination that you want to count, right? There is only one way where this one sit on the top, right? Okay, so that means if you fix number one on the top, then you can only count these 2 pictures only, which is exactly the number you want to count. You don't want to count 6, you want to count 2. Okay, right? For each of the thing that you count, even though you can rotate them all you want, for each of the thing that you count, there's only one way to put number one on the top. And that's the same idea why fixing the head works. And that's how are we good? You can fix the head or you can just divide them by number 10. I think that's, I like division better. I like division. But you can reason about them in many ways. To share access. Uh, go take Ajahn Brian class or something. Philosophy of science. I don't know what it's called. There's a class on philosophy. Whoever asked if the chair exists, Airbus. Are you sure? Is it not just your imagination that I sit on a chair? Then you start asking yourself, do you exist? Okay, so as a programmer, guys, invest on 2 things. Your your chair and your keyboard. Okay, maybe mouse as well. Invest in your chair, trust me, as a programmer. You do. Just trust me, it makes your life so much easier. A really good chair, and you need to learn how to sit like normal, like properly. That's gonna help a lot with your back and everything. Okay, now let's come back here. Let's come back here. So we're gonna let's think about this. There are 10 students. Let's make 15 students. 15 students. Okay, and for standing desk, I'm not sure if it works. So standing desk, that's a questionable thing because I haven't tried though. But good chair, I know the difference. Okay, there are 15 students, and I want to pick five. Pick five to give them an A automatically. Okay, the rest get an F. No, OEA gonna call me if I do this. Okay, let's say there are 15 students. I'm gonna pick five, and then I'm gonna grade, give the rest an F. So the question is, how many ways are there that I can do this? Right, there are 15 students. How many ways are there? Okay, I give you 3 minutes to see if you are the group on the left or the right. Keep up. Okay, Keith, you're on the right already. Okay, let's see how would we reason this. Okay, there are many ways to reason this, and I think some of you learned this in high school, and no one actually tell you why. No one actually tell you why. I'm pretty sure it's rare. Right, what he said is correct. It's 10 C5, 10 choose 15 choose 5, but no one actually tells you why it's a factorial and a whole bunch of things. Okay, so let's reason about this together. Okay, so let's think about this. The thing that we know so far, right? We know how to do permutations. How about the following? I have 15 students. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Let me put 6, 7, 8, 9, 10. Sorry about that. Let me put it here. 1, 2, 3, 4, 5. Okay, so we can rearrange 15 people, right? 15 people, we can do the permutation, right? 15 student, we can do a permutation. Okay, so that means we rearrange this, right? We rearrange, we get the student line up in many different, we count the number of ways student lines up. That we can count, there are 15 factorial of them to get the student lined up. And then I'm just gonna say, okay, the first 5, you get an A, the last 10, you get an F. I can do that, right? Are we good? We can start with that. But you know in your heart, right? You double count like crazy. You double count like crazy. So let's think about how much do we really double count. Is everyone good with 15 factorial? And then I'm going to test the first 5. I'm going to take the first 10, give them an F. Okay. So 15 factorial is a good start. But we overcount like crazy because, for example, if student 1, 2, 3, 4, 5 are here, right? Student 5, 4, 3, 2, 1, right? That's another permutation are going to be here as well, right? And we double count this as different ones, even though we should count them as only one, because that means student 1 to 5 gets an A. Are we good? So how many did we overcount the first section? How many did we overcount the first section? How many do we overcount? How many of these copies are there? There are 5 factorial of them, right? Everyone get? There are 5 factorial of them. So that means we should divide them away by 5 factorial, right? To make sure that we don't overcount the first section. Okay? But then, the latter section, which there are 10 students, y dy and not plus, y minus. Okay, so here's the thing. So let's because for each of the thing that you want to count, right? Each of the thing you want to count this. Okay, for each of the thing that you want to count, you have 5 factorial copies, which is 120 copies that you count within the 15 factorial. Okay. So in 15 factorial, you count 1, 2, 3, 4, 5 in total 120 times. So you want to make the division. Okay, but that's not it, right? That's not it. Because the last 10, let's call that, I don't know, 10, 11, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. You all count these people as well. By how much? What's the factor here that you overcount them by? By 10 factorial, right? Because you can rearrange them in any way you like, right? For each one of the copy that you want to count, you overcount them by factorial times, which is a lot. I don't know what the number is for 10 factorial times. So that means to fix it, you just do this, right? Just divide that by 10 factorial. And this has a name because it shows up a lot in counting. It's the action of choosing. Okay, so we call this 15 choose 5, which is exactly the same thing as 15 choose 10. You can choose whichever one. Okay, so this read 15 choose 5. There we go. Okay, or that Keith said some book do the following, some book do the following. 15C5. I think that's easy. That's so hard to read. I prefer this notation. Okay, so that means the number of ways. Let me summarize this. The number of ways to choose. Okay. Let me put here as well. Order doesn't matter. We choose K item from N item is N choose K, which is, if you look at it, it's N factorial over K factorial, N minus K factorial. Exactly what we discover over here. Is everyone good? Everyone good? And Jack will be so proud. Why? Probabilities. Okay. Now another mystery solved, right? If you see this in high school, no one explained you why it looks like so random expression like this. Okay, it's actually just a division rule. Okay, because you overcount like crazy at the front and at the back, you overcount like crazy. But you should think about this. If you can reduce your problem to choosing, just do this. You don't need to like count how many you overcount again. If you can reduce your problem into choosing, I choose and then I do the following, then just think about choosing. Okay. So what's the answer? That. Which is exactly the same thing as this. Yes, for this one, you just think about it. If you want to know the number of ways you want to choose something, you just write this. Okay, but you should reason why you would choose something. Okay, so let's think about this. How about let me modify it just a little. Why doesn't it go to the next page? Go to the next page. There. What if I have again 15 students, but I am going to be a little bit more lenient this time, which means I'm going to give 3 students get an A, 5 students get a B, and how many left? 8 plus 7, 7 students get a C. How many ways are there? Okay, think about this. You have a trick in the back. If you know, okay, I just need to choose something, then you're good. There is this guy, Saran. Saran, can you put that in Mathematica and tell me if this guy is an integer? I doubt that it is an integer. Saran. So let me say, it's probably not an integer. Or is it? Probably not an integer. So Alexi, they are not equal. Alexi, what do you mean by 15? They are not equal. Okay. So what he said is interesting. He said 15 to 5, so close, yet so far. Okay, any other answer? Any other answer? And now what? And Airbus is 15, 3 plus 12, 5 plus 1. This guy also is so close, yet so far. Okay. Oh, okay. So Alexi is with Noah. Okay. Okay, let's reason together. I think, yes, this one is correct though, 12, 5, and 7, 7. So Keith is wrong with that number, that's all. I think it's a honest mistake, so I'm gonna fix it for you, Keith. Okay, so, and Airbus is actually very close. Airbus actually changed this to multiply on at only change that to multiply. Right? It's exactly the same thing. Except you forgot to multiply, it should multiply, right? So let's think about how we would reason something like this, right? We would reason something like this. So we have 15 students. Here's a process you're gonna do, right? You have 15 students, you pick 3, you choose 3. Let me say, choose 3, give them an A. So that means I have 3 students already for an A. Okay. So that means all you need to do, right, is to choose another 5 to give them a B, another 5 to give them a B. Okay, so choose another 5, but you cannot choose from 15, right? You cannot choose from 15 anymore because you already choose 3. So there are only 12 left. Choose 3 people to get a B. 2, 3, 4, 5. and these people get a B. Okay, and then there are only 7 people left. Then you can say 7 to 7. You can calculate it. It's exactly 1, right? It's 7 factorial, 7 factorial, and 0 factorial. 0 factorial is actually by convention. It's a 1. It's a convention to make sure that the formula looks nice. Okay, so Pascal, so the total waves doesn't matter, right? All these get an A, right? So when you do choose, you don't care about the order already by the way we construct the choosing. Okay, the reason we get this formula, right? We ignore all the orders. We divide away all the orders. Oh, doesn't matter. It's actually the same. You can actually show that they are all the things gonna cancel out. So think all the things gonna cancel out, right? So the answer gonna be you choose 15, choose 3. Whatever you do, there's 12. Oops, choose 5, right? Choose 5 and then 7, choose 7. But Keith asked something very interesting. Ajahn, how about I choose the people who get a C first? Yes, you can. It's gonna be the same thing. This is gonna be exactly the same thing as 15, choose 7, and whatever left, what is it? 9, 8, choose 5, and 3, choose 3. You can calculate, they're gonna show up as exactly the same number. Okay, you can try calculate, it's gonna show up exactly the same number. Actually, a lot of proving that involve factorials is actually done to combinatoric, right? If you count the same thing twice, they better be the same if you count them correctly. Okay, a lot of proofs done through that. Okay, so let's learn something fun. Let's learn something fun. You probably see this before. This is actually called binomial theorem. Okay, you've probably seen the Pascal triangle and so on before, right? So let's say we suppose we want to calculate a plus b to the n, and n is like 20. Okay, and n is like 20. So let's say it's 7. Okay, because I can write 7. So that thing is exactly the same thing as a plus b, a plus b, a plus b. That's 3 already. A plus b number 4, a plus b number 5, a plus b number 6, and a plus b number 7. 2, 3, 4, 5, 6, 7. Okay. So there are 7 of them. And then I want to know, right? You know that when you expand this guy, it's going to come out to a whole bunch of terms, right? There are, I think, how many terms? 14, 15 terms ish, right? But one other term is going to be a to the third and b to the fourth, right? There are a whole bunch of terms, and one of the term is going to be a to the third and b to the fourth. And then you know that there is going to be a constant in front, right? The constant in front. So for example, a plus b cubed is a cubed plus 3a squared b plus 3 plus b squared. So that number 3 is the coefficient there, right? We are interested in the coefficient there. Can you help me find it though? Can you help me find the coefficient here? Okay. Can you help me? The coefficient equals what? This is the question. Not 7, not 7. I can tell you it's not 7. It's a lot. That's a formula. Yes, we're gonna figure out exactly what the formula is through combinatorics. Right? When you learn chemistry, you hope that there's some guy who write a formula somewhere and then you look it up. But now you're on your own. Right? In this class, we don't base our knowledge on like anything. This is probably one of the fundamental ones that based purely on your logic. Okay. So let's think about this together. I think this one, if you see it, then you see it. If you don't, you don't. If you see it, you see it. If you don't, you don't. Gonna take you a while. Okay, think about how we construct, right? Yes, you can move from alpha. Think about how we construct a to the third, b to the fourth. There are many ways to do it, right? So for example, that means you need 3 a's from each parenthesis, right? And then 4 b's. And then 4 b's. So this is one way to do. Oops, let me put it in a better color. Let me use pink. Okay, 1, 2, 3. Oh, we cannot use the same. Right? So think about this. From each parenthesis, right? For each parenthesis, when you multiply them together to get a to the third, b to the fourth, right? So that means when you multiply, you need 3 a's and 4 b's from the parenthesis. Okay, so you can get a from 1, a from 2, a from 3, and b from 4, b from 5, b from 6, b from 7. Okay, or you can get a from 1, a from 3, a from 5, and then b from 2, b from 4, b from 6, b from 7, right? These two also give you exactly the same thing, a to the third, b to the fourth, right? When you multiply them up. Okay, so the thing is, if you try to count the coefficient, right, each one of them can be count exactly once, right? Each one of them can be count exactly once. So each one of them contribute 1 to the coefficient, right? Each one of these contribute 1 to the coefficient of a to the third, b to the fourth. Is someone good with me though? This is a very important concept, right? Can I again? Yes. So then it can't multiply. So let's think about a plus b and a plus b. Okay, let's do like the second power. So that's a1, b1. Let me just put the thing here. a2, b2. So when you multiply them, all right, what's gonna happen is the following, right? You're gonna have a1, a2, right? Plus a1, b2, plus b1, a2, plus b1, b2, right? But you know the thing that, but if you write a plus b multiplied by a plus b, then you're gonna write it's a square plus 2ab plus b square, and that number 2 comes from the fact that there are 2 ways you can do to get a times b. It doesn't matter which a you get, which b you get, right? So each one of these contribute exactly once to the coefficient. Okay, each one of these. Exactly the same idea. If you have 2 to the 7, if you have like a to the 7, right? That's the same idea. You just count how many of them are there. Right? 7 good? Right? Why b can't be the same ones as a? Because when you multiply, right? When you multiply these two parentheses, a and b, these two never get multiplied together. Right? You multiply this and that, this and that. I'm getting to that. Same idea. Right? So the question here is, how many of these are there? How many? Has 4A, and 3A's and 4B. A1, A2, B2. No, we cannot do that, right? Because when you multiply here, when you multiply the two polynomials, right? They do not multiply within, they multiply across. The multiplication is across them. It's not within. Are we good? So that means you choose one here, you choose one here. Oh, anyone? Anyone? So how many of these are here? How many of these are there? Right, so now you know the coefficient is exactly the number of A and B's that you can add up to 4. Okay, let's start with Nawat. Nawat is 7 choose 4 times 7 choose 3. And Alexi. And what you're gonna get at the end is exactly the formula that Keith was mentioning. 7 factorial over 7, that's a 6 factorial. Anyone else? No idea. Okay. Okay. The run is 7 choose 4 multiplied by 3 choose 3. Okay, and Thanatat said, Thanatat, I'm going to call you TT. Looks like you're crying. Okay, let me change. Thanatat is 7 choose 3. And by the way, these two are exactly the same thing. Okay, Thanatat, tell me, how did you get 7 choose 3? What did you do? What did you do? Why did you get 7 choose 3? Good, you have 7 of them, right? This is exactly the same problem as last time, right? I have 7 students. Each one of them, I can give them an A or a B, right? So I choose 3 to give them an A. The rest, you have no choice to get a B. So this is 7 choose 3. Okay, or you can say 7 choose 4. That's the same thing. 7 choose 3 and 7 choose 4 is the same thing. Is that one good? And this is called binomial theorem. Let me write the real binomial theorem. Right? You know the 7 come from here and 3 come from there. Quite clear for you now, right? So the binomial theorem says the following, right? The thing that Keith mentioned, that there are formula for it, right? It's going to be sum of n choose k, a to the k, b to the n minus k. Zero to n. Is that one good, right? By that reasoning, we figure out how to find the coefficient in front of a to the third and b to the fourth. So that's exactly this. What, Keith? What is with A1 and A2 and A1 and A3? What do you mean? That term doesn't exist because you need to choose 7 of them, right? Multiplication, you need power 7. What about it? What's with A1 and A2? What do you mean? Why are there only 2 of them? 2 possible choices. There are 7 choose 3 choices of them. What do you mean there are 2 choices? After class, and I don't get what you meant. Okay, so another thing. Before we go, let's ask you the following. Okay, so let's start with number 0 to 9. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Right? You know that there are how many of them? Like 10 factorial, right? It's quite clear to you there are 10 factorial of them. Okay, so 9 digits. You can rearrange them any way you like. You can rearrange them any way you like, but I want to ask you the following. How many has 0, 4 next to each other? Right, next to each other. Or 4, 2 or 6, 0. Right next to each other. Okay, this looks like the thing that you did before. Something is a little bit different here. That's something I want to teach you. Okay, so let me give you an example. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's bad because it has neither of these, right? But 1, 2, 0, 4, 5, 6, 7, 8, 9. This is good because 0 and 4 next to each other. This is also good. 1, 5, 0, 4, 2, 6, 7, 8, 9. This is also good because there's 0, 4. There's also 4, 2. It should be counted once, right? The domain is this guy. The domain is like 10 digits number. Or this guy counts to 6, 0, 4, 2. Right? There's 6, 0. There's 0, 4. There's 4, 2. So the thing is, you should count it once. Don't count it twice. Like last time I said, there's only one rule, right? Count everything once each. Don't count it twice. Okay, I give you 2 minutes to think about it. No, in this particular order. Okay, so no 4, 0. This actually makes the problem a bit easier. The fact that I fixed the order makes your problem like a lot easier. Alexei, I can tell you, it's not an integer. That number is probably not an integer, right? Because the top part is even, it's not divisible by 3. Maybe, I don't know. Most likely, they're not going to be divisible by 3. Okay, there is Keith, right? There is 8 factorial times 3. Now what? 7 factorial. What did I do? You give the wrong answer or you love giving the wrong answer? Okay, I like this answer though. Know what? It's Keith answer minus 6 factorial. So run is 8 plus 8 plus 8 plus 6 factorial. Wait, minus, right? Minus, sorry about that. You are all really close, but none of you is correct. You are all really close, but none of you is correct. If okay, Thanatat, 3 times 9 factorial minus 3 times 6 factorial. Okay, guys, I can tell you, you four have every single piece of puzzle, but you combined it wrong. if you all combine your answer, you might get the correct answer. Okay, so let's do this because we have 10 minutes. Let's do this. Okay, so I think everyone is, I'm not sure why 8 factorial, where 8 factorial come from though. 0 to 9, there are 10 numbers. There are 10 numbers. Okay, Saran change. What? Okay, let's see. Let's call it Saran 2. 3 times 9 factorial minus 2 times 6 factorial. I have no idea where 8 comes from. Okay, let's ignore the fact that there's an 8. There's actually an 8. You're gonna see. Okay, let me ask you the first question. What is 9 factorial? A lot of you have 9 factorial. What is 9 factorial? What's 9 factorial? What is 9 factorial? Make two number into one number, right? So that means we know that the people who have 0, 4, they are 9 factorial, right? The number who has 4, 2, they are also 9 factorial. And there is a people who have 6, 0, that's also 9 factorial, right? We learned that before. We pack, we arrange, and then we unpack. That's the way we get 9 factorial. Okay, so let's think about this. If we just add the 3, what's going to happen though? What's going to happen, right? There are going to be some of them that I overcount, right? Someone good? Some of them we are overcounting. Okay, so let's draw a Venn diagram. Okay, so 9 plus 9 plus 9 factorial. So there is going to be 3 things, right? Okay, so this thing is 0, 4. This thing is 4, 2. If you win the lottery with all these numbers, let me know. Share some money with me. If you win the lottery with any of these 3 numbers, you have one in about 33 chances of getting it right. Okay, so 9 factorial. Let's think about what exactly did you count? Okay, what exactly did you count, right? 9 factorial, the first 9 factorial, right? For the 0, 4, you count 1, 1, 1, 1. Are we good, right? So that's good, right? So for 4, 2, the second 9 factorial, you add this thing 1, so this thing become 2, and that thing become 2, and this thing become 1, right? So, and then the last 9 factorial, that thing becomes 1, this becomes 2, this becomes 2, and this becomes 3. Is everyone good with the logic, right? If we just add 9 factorial, this is what's going to happen. So how do we fix it? Anyone? How do we fix it? How do we fix it? We start with 9 factorial, add it 3 times. How do we fix it, guys? Everyone good with this diagram, right? That 9 factorial, when you add it 3 times, this is what's going to happen. Right? And then let me write the number here. Just a second. So this thing is going to be 604, right? And the thing inside here is going to be 042. And the thing inside here is going to be 42 and 60 somewhere. Right? And this is 6042. Okay, so the second thing that we can do, right? We can count how many 042 are there, right? So at least we can subtract off this piece, right? 042 is the whole piece like that. 042, I think everyone now know by now, right? It's 8 factorial. 604 is also 8 factorial. And 42 and 60, that's also 8 factorial. Okay, I think everyone knows this by now. Okay, so that means, so let's do what Saran was suggesting. Ajahn, all you need to do, right, subtract off this. So let's subtract off all of them. Okay, so let's subtract them off. Let me get my number back, 2 seconds. Okay, it was 2. Oops. It was 232, right? So when you subtract off, right? When you subtract off the first factorial, 042, what's going to happen to this diagram? Because this guy can become 1. This guy can become 2, right? Because you subtract it off by 1. Okay, at least we kind of have what we need, right? Over here. When you subtract off the second 8 factorial, you subtract off 804, which means this guy gonna become 1. This guy gonna become 1. That's good. But then when you subtract off the last guy, 4260, it is going to become, oops. Oh God. This thing gonna become 1, but this thing gonna become 0, which is not what we want, right? Which is not what we want. So how do we fix it? So how do we fix it? Anyone? We want it to be 1 everywhere, right? Because that's what we want to count. Do you really want to add 3 times 7 factorial? How many of them are there that have 6042? How many of them are there? 7 factorial. So you should add back 7 factorial, right? So that the guy is going to be 1. Okay, and that's your answer. This technique is actually general. It's called inclusion exclusion. You did it in the case of when there are 2. You can actually do it when there are 4, 5, 6, and 7. Inclusion, exclusion. Don't combine your power in the midterm, though. Don't do something stupid. Don't make me mad like Ajahn Kanat. Don't abuse your privilege. I am giving you the privilege. Do not abuse it. Yes, you get partial and you get partial credits. Don't worry. We read your proof. Unless it's like totally off, then you don't get any partial credit. You draw a cat, no, you don't get partial credit. Like Sharon, if you take a picture of your cat, put it in the midterm, you don't get partial credit. Okay. Any questions so far though? Any questions so far? So homework 5 due Sunday and midterm going to be posted early next week. There are going to be about 6, I think 6 questions, maybe plus the bonus or maybe not plus the bonus. But the bonus, don't worry, is typically just for you to have something to think about for the rest of the week. Depends. Like I can make the total any number I like. I can make it 54 100,000. Okay. Any questions though regarding midterm homework and everything? Will there be a carpet problem? What carpet problem? I don't remember. How does 604 works? Oh, you lump this thing as one number, right? It's the same idea. It's a pack and unpack. That means you have 7 other numbers left, right? So there are 8 things that you need to rearrange. You do exactly the same idea, pack and unpack. That's in the homework. Carpet is in the homework. Midterm are not going to be as hard as the homework though. Yes, you can do that because you can call that number t, right? One t, 1, 3, 5, 6, 7, 8, 9, 0. Wait, is that 0? No, no 0. Right? You can rearrange this any way you like, right? 1, 3, t, 5, 6, 7, 8, 9, and then that t is 0, 4, 2 in this case. Are we good? Right, Hanatat? You can see it, right? That y 0, 4, 2 because it has 0, 4, and 4, 2. 0, 4, and 4, 2. That's what we want, right? So in this here is 0, 4, 2. Because it has 0, 4, and 4, 2. There's only one way. It has to be 0, 4, 2. That's why I said in that particular order, gonna make your life so much easier. Otherwise, you're gonna have too many cases. Okay, because I want to show you inclusion, exclusion. Sometimes you need to add back whatever you over subtract. Okay, any questions now? Next time we're gonna do a little bit more counting and then we're gonna start with probabilities. Okay. Okay, let me stop sharing this, stop recording.